So for this week, I guess what's on the agenda to start with is fuel-air mixture. So the fuel-air mixture, I'm going to spend the first part of this talking about gasoline engines. And the diesel engines are pretty similar. They've got a couple other little quirks, but we're going to have to find a different marker. That one seems to be out of gas. So on air-fuel mixture, they like to use a big fancy word called stoichiometric. Let's see if I can even spell that. Well, what that really means, if you remember right, when we were talking about the chemistry of all this, why our fuel, which is hydrocarbons, we have these carbon molecule or carbon atoms in our molecule and our hydrogens out here, and these are long strings of carbons like this. And for this all to pan out right, the way we want it to, we need to have the right amount of oxygens to work out with this. And that's really all this is saying. Big fancy word, but we need to have enough of our O2s. So our O2s is 2 oxygens like this. And we want to have enough of these to balance out with our hydrocarbons. So the ratio that's published is we need 14, and it's actually 14.64, blah, 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 but we're going to call it 14.7 to 1. This is oxygen, and actually that's not quite true. We need 14.7 and this is by mass. So in a lot of the information published, it'll be in grams, but it don't matter if it's grams or if it's in grams or pounds or whatever, but it's actually by mass, not by volume. So it's a little unusual to think about weighing air, but that's actually what they're doing. You can do it in grams or in pounds, but you want 14.7 pounds of air to 1 pound of fuel is the way that will work out to get you the right amount of oxygens to bond up with your carbons to make your CO2 that we want, and the right amount to bond up with our hydrogens to wind up with H2Os. And the deal is, if we have that ratio, we wind up with very little of those other side effects that are undesirable. The carbon monoxide and the straight carbon and the oxides of nitrogen and all that stuff. Now, that's a fine line to try and hit. So if we wind up with a rich mixture, when the term rich is used, unless we're talking to Mr. Rich Needens, we're talking about rich in the term of too much fuel. And when we use the term lean, we're talking about not enough fuel. So in that ratio, if you wind up with it too lean, where we're up to the point where we've got somewhere in the vicinity of, say, 16 air to 1 fuel, there's not enough fuel in the mix to actually keep the flame travel going, and it's really tough to get it to combust and actually produce power. On the other side of it, if we're down where we've only got, say, 12 air to 1 fuel, it's so rich that there again it doesn't make great power, and you wind up with a lot of carbon and a lot of the other undesirables on either side of this. Now, if we're unbalanced within reason, when we're down around in that area where we're at like 14 to 1, it actually will make good power there. It'll actually make slightly better power, just barely slightly, and it's easier to get it to burn when we don't have enough temperature, but it makes a little more of the undesirable side byproducts. So that's just a little bit of a sketch of why we're trying to get things to balance, because we're wanting to make good power but not have a bunch of the undesirable side effects. The results of rich is, there again, we'll wind up, if we've got too much fuel for the air we have to work with, we'll wind up passing through the engine some raw fuel that's not burned, which is hydrocarbons. We'll wind up with a bunch of carbon, which is where that process started to work, but we've got carbon and didn't have any oxygen to put with it to make the carbon dioxide, and we just got carbon. And we'll have some of the carbon monoxide. And you know, you used to hear about people gassing themselves to death in a garage and whatnot. When we were running carburetors, which were much less precisely at this ratio. Sorry, I got a little wild with the eraser, didn't I? Which a lot of times that's done with a colon to one. Carburetors are a lot less precisely at this than some of the more modern fuel mixing devices. So if somebody started a car in a garage and was warming it up on a winter day and weren't careful, they could wind up with too much carbon monoxide. Carbon monoxide implants itself in our red blood cells and sticks there and doesn't exchange in our lungs the way it should, and you can't replace it with oxygen, and you wind up suffocating. And it's known as carbon monoxide poisoning. And you don't hear near as much of that as you did 30 years ago, because the cars that are made currently, they hit this ratio a lot more precisely, and they just don't make near as much of that carbon monoxide as we did when we were running carburetors. On the other side, if we're too lean, we don't have enough fuel and we have excess oxygen, the way the chemical reaction works out, we actually wind up with a lot more heat. Our combustion produces a little less of the pressure to push the piston down than we want, and a little more of the heat. So it winds up being a hotter burn, and we wind up producing more of those nitride or NOx, oxides of nitrogen, which are undesirable byproducts. And the way that reaction all works out, we wind up with a lot of chemical and reaction going on in the catalytic converter. So if it's a vehicle that has a catalytic converter and you're accidentally running it too lean, you can wind up melting that catalytic converter. So that's another reason we don't want to run it too lean. Some reasons we would want to alter that. This works out good when we're at operating temperature. You know, if our engine's actually running at somewhere in there between 150 and 200 degrees, the metal of our engine is in that range. If we got a cold engine, we're trying to get started and running. When our temperature is down, you know, below 70 degrees, and especially if we're down below 30 degrees, boy, it's tough to get that flame to propagate through that mixture. And so we'll enrich it. We'll on purpose make it a little richer to get things started and running. Different systems will do that enrichment by different mechanical means, but you know, stuff that has a choke, that's what the choke is doing. It's actually partially blocking some of the air while letting the fuel free flow, or in some cases creating more fuel suction, to enrich that mixture to make it where that flame can propagate through the cylinder and you can actually get things running and warmed up. The other time that we want to on purpose enrich that mixture is on acceleration. So if we're running our engine at 800 RPMs and now we want it at 1500 RPMs, we're trying to speed it up. Getting that speed to raise works better if we enrich it while we're changing that RPM. Once we get it up to 1500, if we want to stay there, we want to go back to this. But during that acceleration process, when you're sitting at the stoplight and you want to go 60 mile an hour down the highway, when you're going from 0 to 60, we want to give it a little extra gas. Does that make sense, Joe? And once we get to 60, we want to go back to this balance of air and fuel. So the old-fashioned way we did this, which worked pretty good, didn't work perfectly, was a carburetor. So what a carburetor basically is, we're going to have a tube that we're going to suck our air through. And there's a principle called Bernoulli's principle. In science class, they would talk about that. But when you speed the air up, so if we got air coming through a pipe that's this big, and then we choke the pipe down to this size, well, obviously for the air to go through this smaller pipe, it's got to go faster, right? Well, when it goes faster, the pressure decreases. In other words, it creates vacuum or a sucking action. So if we put a little breach here in the side of it, and we run this over to a bowl of fuel, so we've got liquid gasoline in that bowl. The pressure in here is less than the pressure there, so it does the same thing as if we put our mouth on that red drinking straw right there and sucked on it, right? We're going to suck fuel out of this. We got lower pressure here than, and I guess to be perfectly accurate, there would be a vent here. So there's atmospheric pressure here in this fuel bowl, and we've got low pressure here, so we're going to have fuel flowing this way. As it comes out of the end of this tube, with all this air rushing through here, it makes this fine little mist, and gasoline vaporizes pretty readily on the surface. So down here in the middle of the liquid, that fuel doesn't want to vaporize so much, but the vapor that's on the surface here, and that's on the surface of all those little bitty droplets, it turns from liquid into vapor pretty readily. And for the combustion process to happen in the cylinder, it really does not work well when the fuel is still a liquid. And it worked really well once we vaporize that fuel. So there again, we're not working with liquid oxygen and liquid fuel when we're making that explosion. We're working with vapor oxygen and vapor fuel. So Now, so that sucks the fuel up in here and mixes it. So to get the mixture kind of where we want it, what's typically done is we make a restriction in this. So we'll take a wedge-shaped screw, and I'm going to draw this real big and crude, but we're going to take a wedge-shaped screw and put in there against a seat that somewhat matches it. So to adjust the flow of that, we can screw that screw in and make this passage smaller, or if we want more fuel, we screw that screw out and make it bigger. Now, that's the basics of a carburetor. Now, we typically make all kinds of fancy side notes on that, and typically, most of the carburetors you'll find, whether they're on your lawnmower, your 1971 pickup, or whatever like that, they're going to have one of these passages that's pretty small, that's designed with an adjustment for idle. So you can get that mixture right at idle, usually at 700 or 800 RPM, something like that. And then there'll be another bigger one that's what's known, and this is typically known as the idle circuit, and then you'll have a main circuit. So this one, for when you're actually driving down the road at 2,000 RPMs or whatever, is going to be much larger, but it's the same deal. We'll have a screw that we can screw in there and adjust how much we restrict that. You know, as they tried to get, I had a professor in college that said, and this is true, a carburetor is the only thing that's always wrong, because you'll never, ever, ever hit that exactly. Why do you think that might be? What variables are we working with here? That's one of them. Different grades and specific densities of fuel. That's actually not nearly as big of a variable as something else. All the variables in the air, which air pressure is the biggest one. So the air pressure here at this elevation is much different than at sea level, or even at Omaha, or at Laramie. And then given days, it changes here. And the oxygen content in the air changes a little bit. Not a lot, but it'll change from 20% to 22% and back and forth pretty regularly, even within a given day. But the biggest one is air pressure. So what we're talking about it with air pressure, if you have, we'll just take an example of a cubic foot. So one foot cubed. So if you had a block that was a foot by a foot by a foot, and it was full of air, well, that cubic foot is going to contain a lot different amount of oxygen molecules at those different pressures. So at sea level, where there's more pressure compacting it, you're going to pack into that box more oxygen molecules than you are here. And there's going to be less yet if you go to Laramie. And you can read the weather report, and the atmospheric pressure here is different than it was yesterday or last week, right? So the other thing is, okay, these two tubes, this one maybe is optimized for 2,000 RPMs, and this one's maybe optimized for 750 RPMs. So what happens when we're running in at 1,500 RPM? Well, it'll run, and it'll run decent, but it's not going to hit this. What happens when we're at 2,500 RPM? Well, as they tried to make carburetors more accurate, they added a whole bunch of different circuits, and they would add little vacuum servos and electric solenoids, and they got real complicated, but they never can make them quite as precise as fuel injection. So that was one of the main reasons that, during the 80s, most all the automotive manufacturers went to fuel injection. And so there's mechanical fuel injection, and some of that existed quite a while back, but it likewise used preset adjustments to try and hope it mixed with the air that we've got to work with today. The modern fuel injection, the reason it can be so accurate, now a lot of fuel injection systems will have a lot more inputs than this, but this is going to be the minimum inputs for any of the fuel injection systems manufactured within about the last 25 years, which will all be computer controlled. And what the computer is doing is taking information from all these inputs and saying, based on all these inputs, this is how much fuel we need to put in to have that balance right. So the computer-controlled fuel injection, all of those systems I've ever seen will have a coolant temp sensor, and so what it does is tells you what's the temperature of the water or antifreeze coolant that's in the water jacket on top of the cylinder head and around the cylinders. So in effect, that coolant's circulating enough that it's telling you an average temperature of the metal parts of the engine. And the temperature of that is going to affect how the oxygen and how the fuel atomize and how they work. The other one related to the air pressure, they're all going to have a barometric pressure sensor. There's going to be a few of them that are going to combine these two into a single sensor. So this one is the pressure of the air outside the engine that we're starting to work with when we start shoving it in the engine. This one's the pressure in the manifold of the engine. So what we're talking about there is the intake manifold. So there's plumbing here to get from the air filter in through other devices and into these runners that are going right into the intake valve. And many of these systems will measure the air pressure inside this manifold. So they'll have a comparison of what the atmospheric is and what the pressure is right in there just before it goes into the cylinders. The air temperature, why do the stunt pilots like to do their routines early in the morning? And what's the advantage to them of it being cooler? That's true. That is true. And that's one benefit to it. The other one is the air, when it's cool, is denser. So there's more of it to work with. So that same box we were talking about, if you've got a foot by a foot by a foot box of air, even if you don't change the pressure of it, that box of air, when it's 50 degrees, it's going to be condensed, and you're going to have more molecules of oxygen in that box than if that same box of air is at 80 degrees. Because at 80 degrees, it's expanded out, and say if it's all at the same pressure, there's actually going to be less molecules of oxygen to work with at the higher temperature air. So those things are all really important. So the other thing is they're typically all going to work with crankshaft position sensor. Some of the systems are only monitoring that so they know how fast we're turning the engine. Some of the fuel injection systems that are more what's known as sequential, and we'll talk about that more in a minute, they're actually wanting to know exactly what position that crankshaft is at, because they want to fire a specific injector when the piston related to it is at a certain spot in its stroke. This is a big one here. So back in the 60s, a German company, the Robert Bosch company, invented the oxygen sensor. And this oxygen sensor we're talking about is actually put in the exhaust, and it measures how much oxygen is still left in the exhaust after our combustion has happened and we're putting it out in the exhaust. And the deal is trying to hit this number. What it's actually reading is there a bunch of extra oxygen left over once we've had our combustion process or not? And by reading that, they can tell, hey, are we hitting this number or do we need to make an adjustment? And I want to talk more about that in a minute. And then vehicle speed is the other one. And there again, looking at, you know what, I missed one. Yep, I sure did. Right there it is on my list, but I didn't get it on the bar. Throttle position. So like we talked about, when we're accelerating, we want to enrich our mixture a little bit more than when we're just driving at a steady speed. So for example, if it sees that our vehicle speed is 10 miles an hour, but our throttle position is at 90%, well, it knows we're trying to accelerate and go faster, and it's going to enrich it, give us a little more fuel in that mixture. But if it sees we're at 20% throttle and we're at 60 miles per hour, well, it knows we're just cruising along at a steady speed and we're not trying to whoop and spur. So it's going to try and hit that mixture, or it may even lean that out just a little bit. Any questions on that stuff so far before I talk more about the oxygen sensor? Right. Because in the old carburetors, what we had over here, we actually had a device known as an accelerator pump. And what it did is, as you moved that throttle pedal down suddenly, it would take some of this, and through a small, typically diaphragm style pump, it would squirt some fuel right straight in there. And it helped enrichment, and a lot of times what you were doing was kind of making up for maybe a choke that wasn't working so good. Usually you didn't wind up needing to do that much if you had a manual choke and you had kind of figured out how you needed to make it work on this particular vehicle. But the ones with the automatic chokes that maybe were sticking a little bit, pumping it a little bit and giving a little squirt of that right straight into the airflow really helped. On the fuel injection systems, it don't really do nothing, because the computer's taking all of these into account and calculating how much fuel it needs to put in there. And okay, you're affecting this one a little bit, but it's reading all of these and taking all those into its calculation, and is really not going to do much. But if it's working right, it should enrich it, because it knows the coolant temp is low, it knows the air temp is low, and so it's going to enrich it to help get it started, if it's working right, which is a big if, right? So on the oxygen sensor, what we're doing, use your imagination with me a little bit. I'm not paid as an artist on purpose. We're going to call this our engine, and our waste coming out of it, our exhaust that's headed for the back of our vehicle. We're going to put this oxygen sensor right in here. And what it does, it actually creates electricity. And what it does is it compares the oxygen on the back side of it, which is on the outside of the pipe. It compares the oxygen level here to the oxygen level here. And if that difference between the two is very high, it will make more voltage. Now, it makes almost zilch for amperage. Let's take just a minute and talk about the difference between voltage and amperage. Those are kind of on a side subject, electricity, but they're related to what we're talking about here with this and with our ignition system. So if you can imagine your kitchen faucet at home. So how hard the water squirts out of it is similar to our voltage. So if the pressure inside that pipe is 60 psi and you open that knob a little bit, it squirts out pretty good. If the pressure inside that pipe is 5 psi and you open the knob, it may just drip. So the force with which it's being pushed is similar to voltage when you come to electricity. When we're talking about electricity, it's more like the volume of the water. So if you're opening that faucet and you want a gallon of water versus you want a cup full of water, think about that more as the amperage. We're actually measuring the number of electrons flowing when we're talking about amperage. And when we're talking about voltage, we're talking about how hard it's being pushed. So this creates, I don't know, it's zilch point nothing for amperage. That's a relative term, but it's a very minuscule amount. But the amperage is what the computer's looking at. And it actually looks at cross counts. And so on our diagnostic computers we plug in, a lot of times when we're trying to look at figuring out problems, we'll actually look, and all those will have a graph. And the graph this will be 1 volt, and this will be 0 volts. And if we're hitting this ratio of air to fuel just exactly right, that sensor, the difference between the little bit of oxygen left still in the exhaust after it comes out of the engine and what's out here in atmospheric air, will be at the level where it produces just barely under half a volt. It's like 0.45 something, but for practical purposes, we're going to say half a volt. So 1/2 of a volt. So if that's our line down the middle here, in an engine that's working well, you'll actually see this do a wave, and it'll come up above that a little and down below it a little. And many of the softwares that work to mix our fuel actually look at what's known as cross counts, how many times that crosses this 1/2 volt mark. Now, if we're really rich, we've dumped a lot of fuel in there and we're using up all the oxygen, and there's really no oxygen left coming out here, this is going to be right up here. So we're going to see 1 volt all the time because the difference in oxygen between out here and here is high. So when the difference is high, it makes 1 volt, and it'll just stick up here. So how many cross counts do we have there? A big goose egg, right? Yeah, that's what you were showing me, huh? On the other side of it, if we're really lean, so we're not putting really as much fuel in there as we should for the amount of oxygen we got, we're going to have a bunch of oxygen still in our exhaust, So the difference between here and here, and I guess I want to write that down, difference creates voltage. So if the difference is small, because we've actually still got a lot of oxygen in here, it's just going to stay down here doing a bunch of nothing because the difference is small. But in one that we're getting real close to that, and there again, boy, you almost never can hit it exactly perfect. But if you're real close to that and things are all working right, it'll just dance back and forth between, oh, I'm going to say somewhere in that 0.3 volts to 0.7. It'll never hit 1, it'll never hit 0. It just dances right there in the middle, and it'll dance back and forth across this half volt line, and your cross counts will be, there'll be a lot of cross counts per minute. So this oxygen sensor has proven to be one of the most useful inventions ever in fine-tuning our fuel mixture. Now all these other sensors, very important, and these ones which help us figure out how much oxygen we're putting in it to begin with, really help. But all these kind of were easy once we got to figure out, hey, a way to test how much oxygen's still in that exhaust coming out of our engine. I don't think there's been, to the best of my knowledge, any gasoline automobile manufactured in 35 years that didn't use these, because they're really useful in that fine-tuning process. Now, one more thing of interest while we're on the subject of oxygen sensors. What's commonly being done for the last, I don't know, 15 years at least, is so there'll be an oxygen sensor right up there near the engine. Then we're going to have this catalytic converter, which is a device engineered to take some of our incomplete combustion. It'll take our hydrocarbons that went through the engine without getting burned, and it'll also take our NOx, and they're only partially successful at controlling the NOx, but on the hydrocarbons and also on the carbon monoxide, this catalytic converter is really pretty successful at taking that stuff and finishing the reaction we wanted to begin with, so that when we have those things coming in this end of it, we've got our H2O and CO2 coming out here. That's a little side note on catalytic converters and what they actually do. An interesting little footnote there, if you've ever stood near the tailpipe of a car and it smelled like rotten eggs, that's pretty stereotypical of a catalytic converter that's having a lot of raw hydrocarbons shoved in the front of it, and it's actually working. Mistakenly, people have thought that that was a malfunctioning catalytic converter. It's actually a catalytic converter doing its job when the fuel mixture's out of whack and it's getting a bunch of raw hydrocarbons shoved in its throat. So in that case, you don't need to look for a new catalytic converter. You need to go look, see why our fuel mixture is out of whack. And there again, they'll be incredibly hot, because there again, the burn of the fuel, the combustion that we normally wanted to use in the cylinder, well, that burn is happening in here, and you get a lot of heat. It actually creates some really high temperatures. You can have 12 or 1400 degree temperatures there, and those have been known to start some fires, as you can imagine. You put cheatgrass against a 12 or 1400 degree can of metal, and you've got a grass fire, don't you? Well, because The platinum coating that's on the honeycomb in here, if it got coated with lead, it couldn't react anymore, and it was just dead. It wouldn't do anything. So because basically what's happening, there's a real fine honeycomb of ceramic, and it's got a coating of a special metal that's partially at least platinum that they've found works well to initiate the completion of that combustion. And you take that coating and you coat it with lead, it's no longer touching the exhaust flow. It's sealed over and it doesn't work. And the lead was actually an additive put in gasoline to cushion the valves, is what it was, since we're on the subject of leaded gasoline, which is something that's of years gone by. So here we go. When this valve is coming shut, and it's doing so pretty rapidly, why this metal face slamming against the seat was an issue, and they found that with some lead in the gasoline, that lead, which would, there'd be just trace amounts of it here on this surface, but it cushioned that valve slamming shut. The advances in metallurgy, the metal these valves are made out of is incredibly better than what it was 50 years ago, and honestly, that cushioning effect's no longer necessary. And I don't know which came first, the chicken or the egg there, but when they started having to install catalytic converters to clean up tailpipe emissions, they had to pull the lead out because they couldn't make it work with the lead. And about that time is when they came out with a lot better alloys that the valves didn't have to have that anymore. Because what would happen actually if those vehicles that were designed to run with leaded gasoline, if you ran them without, it would just pound the face of this valve off, and the valves would no longer seal because they were beat to death. So whether the better metal came and allowed them to use catalytic converters, or the catalytic converters came and they had to do this, I'm not sure. Like I said, which one created which or what there, but they both kind of came in at the same time, more or less. So anyways, what's being done with most all vehicles made in at least the last 12 to 15 years, they're putting another oxygen sensor in back here. And so what the computer's actually doing is comparing the reading coming from this, what's actually using this one to manage the fuel. This one is not used whatsoever to manage the fuel injection. But what it is used for is to tell the computer if this catalytic converter is working. Because if it's working and cleaning up the last of our incomplete combustion, then there'll be a difference in the reading of this sensor and this sensor. If these two are reading the same, this catalytic converter isn't doing anything. So when it codes for downstream O2 efficiency, what it's really saying is, hey guys, we know the catalytic converter ain't doing nothing, and it's dead, and if you want this light off on your dash, you're going to have to replace the catalytic converter. So, in the 80s, those catalytic converters plugged up really bad, and they were pretty restrictive, and a lot of us would take and saw them out of our pickup, and no ill effects, other than we were emitting more pollutants than we should. But as far as the pickup, how it ran, there were no ill effects. If any of the vehicles that have the downstream O2 sensor, you cut that cat out, it's going to nearly immediately turn on the check engine light for a catalyst efficiency code or a downstream O2 efficiency code. And to get that annoying light shut out, you're going to have the cat. But there is a broad misconception that this one is also part of figuring out the fuel mixture, and it is not. All the fuel mixture adjustments being made are off of this front one. I think that's all I had to say about that, unless anybody's got another question. It's all about how that fuel vaporizes and goes from the liquid state to the vapor state. Well, I shouldn't say all. That's where a majority of it is, and some of it relates to, when we were drawing out that carbon string with the hydrocarbon or the hydrogens off the side, the different octanes have a little bit longer or shorter string, so there's more available energy in them. So, for example, the avgas that's 102 octane, you compare it to the 85 octane that we might be buying at the pump, there's going to be more available energy in it, and it's also going to vaporize from liquid into the vapor easier. Well, airplanes that are running at high altitude where we don't have a lot of oxygen to work with and typically low temperatures, getting that fuel to vaporize from liquid into vapor is a really important thing. There's a long chemical explanation for that, but that's kind of the gist of it. So back to our thing about fuel injection. So as the fuel injection systems have advanced, so initially we would have a carburetor, or some of the hot rodders would have multiple carburetors, but typically the stuff that us common guys would drive would have one carburetor, and it would have an intake manifold, which by definition a manifold is something that plumbs multiple inlets or outlets to a single pipe. And so if we had, for example, we'll just say a 4-cylinder engine. So we've got our 4 cylinders down here. And we need to get our air-fuel mixture into all of them. Why, we'd have a manifold that would plumb those all together to this single carburetor. The early fuel injection systems just replaced this carburetor with a fuel squirter up here that was controlled by the computer, and it was a big advancement over the carburetors. But if you can look at, some of the manifolds were about as crude as my drawing. If you're squirting fuel right here, we don't get exactly the same air to fuel ratio at this point as we did at this point, as we did at this point, as we did at this point, because of the variableness of how it flowed to get to those cylinders. So the more advanced fuel injection systems are actually, instead of, and this was known as throttle body injection, is what that was called, when you had a single point of entry for the fuel up here. So what they call multi-port fuel injection is actually going to have a fuel injector right here, and a fuel injector right here, and a fuel injector right here, and a fuel injector right here. So it can actually control the amount of fuel going into each cylinder, and it winds up being much more balanced than the throttle body fuel injection was. Does that make sense, I hope? Then the next advancement was, so in the early systems, this throttle body injector, it sprayed all the time. Now there was a lot of controls that controlled the pressure and whether the valving in it was wide open or restricted, and so it controlled the amount of fuel, but it sprayed all the time. And when this valve was open, why there would be a surge going that way, and when this valve was open, there'd be a surge going this way, and as the different cylinders valves open, there's a lot of pulses back and forth and a lot of turbulence in here. And that turbulence actually helped to atomize the fuel, but it didn't necessarily help keep even fuel delivery to the different cylinders. And the same thing when they first started doing multi-port, putting all these injectors down here, the earlier multi-port systems, those injectors sprayed all the time. Well, you can see, well, if you looked, you know, last week we talked about how long our intake valve was open here. Well, it's open for the entire intake stroke, plus a little bit on each end of it. So a little bit over 1/4 of the time, this valve is open for air and fuel to flow into this cylinder, but the injector was flowing all the time. Well, not the best, but it was still an improvement over what we had before. So what's commonly done now is known as sequential multi-port fuel injection, which what they're doing, the computer's only firing this injector when this intake valve is open. So when there's actually airflow coming down this runner into the cylinder, we're going to squirt fuel at that point. And when it's not, we're not going to squirt fuel there. And so after that, why his buddy over here, this intake valve opens and we've got airflow here, we're going to fire that one when there's airflow to this cylinder. And that has proven to be a really efficient way to do it, because when you fire this injector while this valve is shut, you wind up puddling a little bit of liquid fuel in the, these are some of my reminders to help me try and stay on time, fellas, but you wind up puddling some liquid fuel over here because there's no airflow moving and we're not atomizing that liquid into vapor fuel. And then the valve opens and we got a suck of air and it'll suck that all in, but some of it may have puddled and may still be more liquid than vapor. We're talking minuscule amounts here, but at the same time, when we're trying to get best efficiency, we want all that to be vaporized. And so there again, the fuel mileage was helped, as well as the emissions were helped when they went to the sequential multi-port fuel injection. So when this cylinder is getting air and needs fuel, we open that injector right here at this cylinder. And when it's not, we're going to shut that one and we're going to open one somewhere else that needs it right now. Does that make sense? Interestingly enough, that is more or less what's always had to happen in a diesel engine. Because if you remember what we were talking about earlier, in the diesel engines, we're compressing all that and getting our temperature high. And then when we're ready to fire it, we're squirting the fuel injector. And as the fuel comes out of it and as it vaporizes from liquid into a vapor, it burns. So we had to inject the fuel right when we wanted the combustion. So typically in the diesel, the injector's actually pointed right, the tip of it's right in the cylinder. On this cylinder head, you can see this is the bore where the injector goes. And the tip of that injector comes through this hole right into the cylinder. So we're actually spraying the fuel directly into the cylinder when we want combustion in that cylinder. So the diesel engines have always been sequential multi-port fuel injection. An interesting side note, I was looking at some of these books from when I was in automotive school, and a few things have changed in that was in the real early 90s, and diesel engines at that time were mostly what are known as pre-combustion chamber engines, or PC engines. So if this was your cylinder, your piston sets in here, of course. What they would have is they would have, typically off to one side, they'd have a little chamber like this, and the injector would spray the fuel right in here. And in many of those engines, the glow plug that was used for extra heat on startup was also in that pre-combustion chamber. But they would squirt the fuel in there and get this all swirling and vaporizing and get that combustion started, and then it would come out here. Now, I didn't probably do the best job of drawing that, because when that happens, the piston, there again, we're talking high compression engines, 18-to-1 or something like that. So this piston is up here where there's very little space in here. And at that time, most of those engines were built with flat heads and flat top pistons, and they needed to get this swirling action going to make the combustion start and start that piston traveling down. So they did it with these pre-combustion chambers, they called them. And it worked, but it was found to work much better when they moved that combustion chamber into the piston top. So you can see the injector spraying here, and it sprays kind of a cone-shaped mist of fuel. And the fuel, so if we take this piston, I'm going to draw another one over here. We take this piston, and we've got a chamber like this, and I guess all of these I've ever worked with actually have kind of a point there in the middle. And we're going to spray our injection right here, and it'll come out like this, and it actually swirls like this. So it goes down near this raised point in the middle, and it actually comes back up around the edges, and all the way around it you've got this swirling action that gets all the fuel mixing with the oxygen and vaporizing from liquid into vapor and starting the combustion process. And so these are called PC, or pre-combustion chamber engine. And these are called direct injected. There are a few gasoline engines doing this as well, where they're spraying the fuel directly in the cylinder, but very few. The majority of them are spraying it in the manifold just before it enters the intake valve. And this is proven to be a much better system. It actually, the way it flows from this chamber into the main cylinder as that piston's starting down and the flame travel is propagating throughout the air fuel mixture, it makes much more even pressure, and it makes better power and less emissions because we've got less what's known as quench area. When all this metal here is a little colder than the main reaction, and basically all the metal that is in the surface of this reaction, it actually quenches that flame travel. And so the more surface area there is of metal touching our combustion, the more what we call quench we have, and the less perfect reaction we have, where we're going straight to the power we want to create and the carbon dioxide and water with less of the trash we would rather not have. A lot of the trash and side effect that are undesirable happens at what's known as the quench area, all the surface of metal that's touching our combustion. So interestingly enough, a lot of the engines that you may have, well, for example, all the Ford diesel engines up through mid-year 94, were pre-combustion chamber engines. All the old 6.9s and 7.3s that were not Power Strokes. Whenever Ford went to this direct injection system is when they started using the name Power Stroke. And that happened actually mid-year 1994. About the same time is when GM changed. Actually, I think it would have been in 93, but all the 6.2 liter Chevy diesels were pre-combustion chamber engines, and the 6.5s were direct injected. And of course, everything made and everything I can think of made since that time has all been direct injected because it works way better. So before I move on to ignition, any other questions about fuel air mixture stuff? It's very slightly different, but I mean very slightly. I want to say it's 14.54 or something. But there again, it's because the molecule of diesel has a different number of carbons and hydrogens to work with in the reaction. So no, it is not exactly the same, but it's real close. It's still 14 point something. I'm sorry, I don't remember off the top of my head the something. So when we talk about ignition, what are we talking about? Anybody want to throw out an idea? Say that? Yeah. Bingo. Igniting the fuel. That's actually a really good way to put it. Which we got to ignite the fuel to start the engine, right? But that's what we're talking about. Now, in our vehicles, we will have what we call an ignition switch. And where that name came from is the system that ignites the fuel. When we turn that ignition switch to the off position, that's typically what we're doing, is we're killing the system that ignites the fuel. Now, in the computerized fuel injection systems, we're also shutting that off. But of course, in the carbureted systems, we weren't shutting the fuel off. We're just shutting off the source of spark that ignited the fuel. So ignite, ignition, similar terms. So in our gas engines, we're going to do that with a spark plug, which typically we're going to stick right in here in the top of our cylinder. And it's going to have it's going to have a center electrode that's going to be connected to our spark plug wire. And what's actually going to ignite that fuel air mixture is when we jump a spark across this gap in the spark plug. I thought I had one of these where it would screw out, but it screwed out and gone. At any rate, sorry, but I hope most of you are familiar with what a spark plug kind of looks like. Drawing it in giant scale, you're going to have the metal section here. That's what screws into the engine. You're going to have a center electrode that sticks out kind of like this. And then we're going to have what's called the ground electrode over here. There's actually going to be ceramic insulation inside of here that insulates this center electrode from this metal shell so that we can have electrical power coming in here and jumping this gap and than being grounded through this side one. So when that spark jumps that gap right there, that spark is what's igniting our fuel. When we're talking about voltage and amperage like we were before, now remember, we've taken on our compression stroke and we've compressed our air. So compared to atmospheric pressure air, like what we're breathing here in this room, once we've compressed that, there's way more air molecules and some fuel molecules all in this space that actually inhibit the flow of electricity. So it takes way more voltage to jump that gap in the compressed atmosphere of the cylinder than it does out here at atmospheric. So typically, the current going in here is going to be above 10,000 volts. In some systems, that can run as high as 65,000 volts. But as far as the amperage, it's nearly nothing. I want to say something in the realm of 1/100th of an amp. It's very, very little. So it's one of those things that you get a hold of that, it really bites and stings, but there's not enough flow there that it's really terribly harmful. Not the kind of thing that, like if you get a hold of the REA pole, it's not going to fry you to a crispy critter, but it's going to sting and it's going to get your attention, make you jump pretty good, won't it? So I wanted to talk a little bit. There's basically two common ways we create that voltage and that spark. The earlier systems, which are still used a little bit today, but typically only used in applications where we don't really want to have a battery, like a chainsaw. You really don't want the weight of a battery in your chainsaw. And a few other things like that is a system that's generically referred to as magneto. So what we're doing, we're going to take this wire. Now there's going to be a common ground tied here, but we're going to have an iron core here, and we're going to have a winding around it. And this winding is going to be hooked over here. Now, you guys remember science class when you were in grade school or junior high? What happens if we take a magnet, let's pretend this is a magnet, and we swing it past that? Right. The magnetic field that's around this magnet swinging through this winding actually creates a pulse of electricity. So actually this engine here's not a bad example of that. On the flywheel here, which turns, we've got a permanent magnet here. And mounted on these two was actually the coil, which I think this might be the one from this engine. Sure enough, look at there. So when we pass that magnet past this coil, the magnetic field of this going into that space and then exiting that space creates an electrical surge in the winding that's in this coil. And so what they do is in the process, if you look right here, right, is that where that mounted? You know what? I don't think the keyway is in this, where this is actually on the crankshaft in quite the right spot. But anyways, what's done is right when they want the spark happening here, as far as where the rotation of the engine is, well, that's where they put the permanent magnet on the flywheel. So that right when it passes by here, and you can actually feel it, see the magnetic field is holding it on there right now. But if you really wanted a jolt, why, hook up to this and we'll pass it by there, and there'll be a pretty good electrical pulse coming out this wire. So the advantages to that, it's a pretty simple system. There's not a lot of complications there, not a lot of things to go wrong, not a lot of parts to manufacture. The drawback to it is it's not adjustable. And we really want, for best efficiency, at different engine RPMs and different load conditions, we want that spark to happen at a different time. A lot of our automotive engines will have the ability to adjust that spark timing from about 5 degrees before top dead center to about 30 degrees before top dead center, depending on engine RPM and load conditions. And there's no great way to adjust that. So for certain things it works okay, but in our automobiles, we typically want to be able to adjust when that spark happens. So what's typically done in our automobiles, these are actually concentric, one's inside of the other, but so that this is less confusing, I'm going to draw it with them side by side. We're going to have another iron core here with a winding like this, and we're going to take this side of it and go to the positive terminal on our battery. And we're going to take the negative side of our battery and come up to here. So when we've got this flow through this, we've got a magnet here, and it's creating this magnetic field, and I'm behind. I was supposed to have been done with this part by now, but we're creating this magnetic field, which is also occupying the space of this coil. When we break this, that magnetic field collapses, and a neat scientific fact is as it collapses, it produces current in this coil. So this, in automotive coils, is known as our primary coil, and this is known as our secondary. And they're actually made one inside the other. So they both are around the same iron core, one inside of the other. And it works incredibly well. Now, in our early vehicles, what we would do is we would have a set of mechanical contacts here. We'd have a little point there and a little point there. And we would run inside what we call our distributor, we would have a cam, same as our camshafts that we were looking at the other night that run our valves, which is a round shaft, but it's got a bump on it on one side. And when that bump came around, it would open our points. And a common misconception is the spark doesn't happen when we close the points and energize them. The spark happens when we open the points and this magnetic field collapses. So if you're looking at the correct direction of rotation, you'll have this spark happen in your cylinder right when these come open. That's when the spark is created, not when they're closed. Now we would also have a tendency for this power right as these come open. Anytime you've taken two wires and held them together, when you pull them apart, that electricity tries to keep flowing for a while, and you get an arc there, don't you? You've got a spark, and that spark jumping across these as they open would burn and pit these contacts and wreck those points. So you may have heard of a device called a condenser. Well, the condenser, what it did, it was a little can over here that was made to absorb that pulse that was trying to jump here. And if your condenser was in good shape, it would absorb more of that, and you'd have less of this arcing and burning here, and your points would last longer. But in this type of a system, which we haven't seen in anything manufactured in automobiles since 1975, I think, you were looking at, and of course this was in combination with carburetors, but you were looking to replace these points and replace this condenser and adjust how they were operated every 10,000 miles. And likewise, because of the inaccuracy of the carburetor, you'd typically have enough carbon buildup, and some between the carbon buildup and some because of the excessive heat whenever the engine was lean, the spark plug would be trashed. So we were looking typically every 10, if everything was really good, maybe 15,000 miles, you were looking to take your vehicle in for a tune-up. And a tune-up primarily included replacing these spark plugs, replacing these points, replacing this condenser, and making some adjustments to all that and your carburetor. How long do we typically run spark plugs these days, guys? Any guesses? Most of the owner's manuals of stuff made in the last 20 years is going to say replace those spark plugs at 100,000 miles. And this is a little side note, but if you do not go to Napa CarQuest, AutoZone, or Junk O'Reilly's or whatever like that, you actually buy the correct spark plug that's the part number from the manufacturer. They'll last 100,000 miles. You go get stuff from the parts store, you don't be surprised if you're fighting weird problems in half that amount of time. And at some of the parts stores these days, it is actually possible to get exactly what the original equipment spark plugs were. It may not be easy to do if you don't go in there armed with the knowledge of what you actually want, and you just let the guy behind the counter feed you what he thinks is his favorite stuff. But all these components are engineered to work together, and if this spark plug isn't what was designed to work in this system, it's slightly different, it's not really going to work the best. The other thing that is critically important in modern engines is you don't put these in with your ratchet and your breaker bar, you put them in with your torque wrench. The exact tightness that these are put in is pretty important these days. These spark plugs are not nearly as robust as they were at one time, and you used to put them in about that tight and it was fine. There's one spark plug that I'm familiar with that the torque spec is 22 foot-pounds, and I can tell you from experience it will destroy that spark plug at 26 foot-pounds, and if you're below about 16 or something like that, within the first month it'll rattle loose and come flying out of there. And when it comes flying out of there, it takes half the threads with it, and you've got a major engine repair. So use the right spark plug and use your torque wrench if you're fooling with spark plugs, is my 2 cents worth. So on our more modern vehicles, what we're doing is instead of these mechanical components, we're actually connecting these wires to the computer, and we're letting the computer fire this coil and send spark here when it needs to, and it's calculating that off of that whole list of sensors we were talking about earlier. The majority of those same sensors that are being used to figure fuel mixture, we're also using to figure out exactly when we want that spark to initiate our combustion. And I guess a little deal there on you've heard of a distributor. All the distributor does is it was a mechanical device, which you do not have in any modern vehicles, that had a spark plug wire here that went to the cylinder we wanted to fire at one time, and this one went over here. and there was a rotating shaft in the middle of it, and we would have the wire from this coil that makes our spark coming in here to the middle of it, and then there was a rotor, it's called, that would point like this, and it had a contact that connected this contact and this contact when we wanted this cylinder to fire. And then it rotated. So and it was connected to the camshaft in almost every case because it needs to turn at the same speed as the camshaft, which is half the speed of the crankshaft. Because there again, for every 2 crankshaft revolutions, we want the spark plug to fire once, right between our compression and our power stroke, right? So, in almost every case, this distributor was connected to the camshaft and turned at exactly the same speed as the camshaft. And there again, those components would wear out. What's typically done in most modern engines is instead of having one coil that makes the spark and connecting it to this distributor to send it to the right place at the right time, we're just putting a coil on top of each spark plug. And so then every cylinder has its own coil, and we're connecting these wires right here from our primary winding in that coil to the computer. And so when it wants this cylinder to fire, it breaks the circuit to the primary winding in that coil on that cylinder. And so you don't have distributors, you don't have distributor caps and rotors anymore. So I guess the other subjects that were on the agenda for tonight was lubrication, and I'm going to hit that for about 3 minutes, because I don't think there's a whole lot that's terribly complicated about it. Fact is, if we have 2 metal pieces and they're moving against each other, they're going to trash each other if we don't have some lubricant between them. So all the moving parts in these engines need to have some lubrication, and we do that with motor oil. And all the modern engines are pumping it. Some of the early engines just had what was known as a slinger. So on our connecting rod, there'd be a little finger down here, and every time it came around, it would dip in the oil that's in the pan and splash it around everywhere, and you kind of hoped it splashed where you wanted it. And a lot of them did a fair job, but definitely not as good for long life of all the bearings as if we pump oil to each one of them. So there again, we talked about our engine block, we talked about how there's passages bored through it, and we're pumping oil to all of those components. 2 little things that I wanted to talk about on that. So we're going to draw, most all our automotive engines are going to have an oil pan on the bottom, and we're going to have liquid oil in here. We're going to have a strainer that's kind of like a coarse screen here, and a pipe coming up to our pump. So the pump is going to be above the level of the oil, and it's going to suck the oil up here. There were a few engines that had troubles with this. If you can imagine, if there's a pinhole right here, same deal as if we took our drinking straw and poked a hole in it, what comes out of the top? All liquid or air? So if you either have a crack in this pipe or a rust hole in this pipe, or there's a joint in it with a gasket and the bolts have come loose, it's going to suck air. If it sucks air, you got a bunch of air bubbles in the oil, the parts aren't getting lubricated like they should, and there's going to be some failure there. Very little of that do we see. There were a few engines in the 50s and 60s that had some problems with that. Once in a blue moon we'll see it these days, but it's usually in an engine that's previously been apart and likely not been reassembled correctly. Pretty small problem. So we've got our pump, and it's typically the next item that it will go to is known as a pressure relief. The pressure relief valve does just what it's talking about, because engine oil or any oil changes thickness a lot based on temperature. So engine oil at 30 degrees is way thicker and way harder to push into our different bearings, and likewise escapes out of our different bearings way slower than oil that's at 200 degrees. So this pressure relief valve is especially important until the oil gets warmed up to normal operating temperature. And what it typically does, a lot of these are set to somewhere in the ballpark of 60 psi. Anything above that escapes and gets sent right back to the pan. And so everything past it is going to be at that preset pressure. The next thing in our lubrication is typically a filter. Most of you have seen oil filters, and the idea there is to catch any debris and trash that may have wound up in the oil. We had a lot of debris and trash back when we had carburetors. We had so much carbon that you'd have a lot of crumbles of carbon making it past these piston rings. Well, anything that makes it past these piston rings winds up in that oil pan. So there was typically a lot of carbon and a lot of ash, and acid that would wind up in the oil pan, and it was catastrophic failure if you let this thing plug up and bypass. But anyways, then there's typically what's known as a bypass. So this here is going to moving parts, I'm just going to say. Because there's going to be pipes from here go to everything we want to lubricate. But in case this filter gets plugged, most engines, not all, but I'm going to say well over 90% of them, are going to have a bypass. And it's typically set at a pressure just below this. So if this is at 60 psi, this is probably at 55 or something like that. Which the idea is, if this filter gets so plugged, we would rather have unfiltered oil go to lubricate all our parts than no oil. No oil is going to trash them faster than oil that hasn't been filtered. It's still a bad deal, but it's not as bad. Does that make sense? So this is known as the bypass. You know, been a long time since we've seen any dramatic, widespread problems with any of this stuff, but that is the basic system that most all automotive stuff has ran for probably at least 50 years. Quality of oil filters is a much discussed subject. And I would say, if you think about how much an engine costs, spending an extra couple of bucks to buy a good filter versus a cheap junk one is money well spent. One example of that, you know, I happen to work with a lot of Cummins engines. The Cummins engine company recommends basically any quality filter, but they have a list that says Wicks, Donaldson, Baldwin, Fleetguard. There may even be a couple of more. If you go to your local parts store, and it don't even matter which one, and they'll typically have a good quality filter and a cheap one. For example, if you go to the Napa store, they'll have a gold and a silver is their way of doing things. The gold filter is made by Wix. It's on most everybody's approved list. The silver is made by whoever bid it cheapest this month. Typically Perlator, Fram, or Mighty, which are all junk filters. I wouldn't recommend buying them, they're junk. The good filter is going to cost you $2 more. Your engine costs thousands of dollars. Don't gamble it on a cheap filter. As far as the oil goes, there again, another one of those things, man, don't let your next door neighbor tell you that this snake oil from the Magic Company is your greatest friend. Put in it what the engine manufacturer designed it for, and you'll have way better success. Any other questions on that? What's that? Oh, I thought I heard something. So the last thing on the agenda for tonight was cooling system, and I'm going to be specifically talking about water cooling, although we'd already talked a little bit about air cooling. These two engines are air cooled, and of course they've got those fins on them, so there's more surface area here, because as the metal heats up, we're wanting to transfer that heat from the metal to the air, and the more surface we have to work with there, the better that heat will transfer. That is exactly the same thing we're doing with our radiator. In the radiator, we're actually passing water through tubes. You may not realize it, but a radiator is actually a bunch of tubes. Most all modern radiators, the tubes are running horizontally, and they're what's known as cross-flow radiators. In years past, we had downflow, or vertical flow, where the tubes would go this way. I haven't seen hardly any of those in a long time. But anyways, the tubes will go this way. The heat will transfer out of the water into those metal tubes. Those metal tubes all have a whole bunch of little fins like this, and the heat transfers from the water, we're going to call it water, it's a liquid glycol-based mixture, into the metal. Then from all those little fins, it's going to transfer from the metal into the air. Because we have way more heat than we can work with, we need to get rid of it. So there again, if this is our engine, most all engines on the front end of them are going to have a pump. That pump is going to push the water back into the engine around all the cylinders. We were looking at it out there, how it goes around all the cylinders. It goes over the top of the head. All the excess heat we're making in that cylinder, we're transferring it into the water. That water is going to flow up into the cylinder head. It's going to, somewhere in the cylinder head, have an outlet. And right here, we're going to have a device called a thermostat. And it's basically all a thermostat is a valve. And whenever the water inside here reaches a predetermined value, which, for example, 192 degree thermostat is a common thermostat. When the water on this side of the thermostat reaches 192 degrees, it opens and lets the water escape out this top radiator hose and comes here to the radiator. We're going to go down through the radiator doing what we talked about there. We're going to transfer the heat from the liquid into the metal fins, from the metal fins out into the air, and then the water is going to come from the bottom of the radiator, which there again, because heat rises, our coolest water is going to be here in the bottom. It's going to come back into this pump and be circulated back through the engine. Now, there's not actually, when this valve is closed, there's not going to be much flow from the radiator into the engine, because there again, our whole combustion process works much better with some temperature. We don't, typically that whole combustion process does not work well below about 170 degrees. And in most designs, 185, 190 degrees we'll have way better fuel efficiency and less emissions. And so we want to keep the temperature this up somewhere in that, like I said, 192 degrees is a common one. So whenever this is closed, this pump is actually just stirring and mixing the water in here. It'll push it. There'll be a little bypass hose that comes here, but we're not actually circulating through the radiator. Does that make sense? Then whenever it gets up to the temperature that the thermostat's designed for, it'll open, let the hot water come out here, let cool water come in here. The radiator is our point of heat transfer, getting our heat out of the water and into the air. An interesting fact that a lot of folks don't understand is as long as you've got about 30 miles per hour of air speed going through that radiator, it's going to cool as good as it was designed to. Now, something you got to keep in mind, if you're traveling east at 60 miles an hour and the wind is blowing east at 60 miles an hour, do you have much airflow through that radiator? No. However, as long as you've got 30 mile an hour of air movement through here, a fan is totally unnecessary. So most vehicles will have a fan. Some of them will be have a thermal clutch or an electric clutch, or some of them simply are run off an electric motor. But everything made in the last 30 plus years, there'll be a fan there, but there'll be some means of turning it on and off. And when that fan is actually necessary is when you have less than 30 mile an hour of airspeed going through the radiator, and you need to get some airflow through it to have some cooling. So, for example, when you're on the highway headed from here to Cheyenne, and the wind isn't going the same way you are, and you're driving 60 miles an hour, you won't be able to tell the difference if you have a fan or not, because it's doing nothing. Any other questions about water cooling? If you think of any, go right ahead, but I'm going to start passing out the quiz. Yeah. Yeah. Good idea, Wayne. Would you do me a favor, Cole, and hand the rest of those out to the back row for me, please? So I'm not a chemist, and I'm not going to be able to tell you a whole lot about how synthetic oils are made. But the big difference we see between synthetic oils and natural coming out of the oil well, ground oils, is they don't break down as fast, and most of that breakdown tends to be heat related more so than friction related. Where we see a big difference is in the gear oils. We'll typically with natural oils, by the time you get 50,000 miles on a rear end, that oil's pretty well trashed in that gearbox. And you rub it between your fingers, and you rub new oil between your fingers, and you can feel a dramatic difference. With the synthetics, boy, a lot of times we can see it go twice that long. Some of it depends on how hard the truck is pulled and that kind of thing. Same thing with the automatic transmission oils. The regular Dextron, which is mineral based, typically, even if you were being really nice to that automatic transmission, you rub it between your fingers when it had 20 or 25,000 miles on it, and you rub brand new with the same exact oil here, you could feel a dramatic difference in the lubricity of it, you know, how slick it was. Um, with the synthetic oils, you can go twice that long in a lot of cases. So what we're actually seeing, so in the old days, you were actually needing to change that oil in a lot of those because it had broken down and wasn't really lubricating well anymore. These days, rarely do we change it for that reason. We're usually changing it because of contamination. It's got too much soot or acid or water or other contaminants in it. But boy, we sure don't see it break down the way it used to. Another thing that we've really noticed is in wheel bearings, the ones that are oil bath wheel bearings, which typically the ends of most of your free-floating rear ends are oil lubricated, not grease pack. Boy, the ones with synthetic in there, when you have a leak and that thing gets low on oil, they're a lot more forgiving about that before they go up in smoke and stuff starts getting chucked in the scrap iron bin with the synthetics, because that synthetic tolerates the excessive heat much better before it breaks down and ceases to lubricate. I'm sorry I don't know a lot about how those synthetics are made, but I guess that's just my observations on what we see with using them. We don't see a lot of benefit to the synthetic motor oils, because there again, in most cases, even the natural motor oils, and there again, I tend to live in the diesel pickup world, and specifically the engine oil that's specified in a lot of those was the Rotella 1540 that was a natural mineral-based oil. And there are some of the newer engines that are specifying the T6 Rotella, which is a full synthetic. They make a T5, which is a blend of the two, and I don't really see the point of that. Pick one, but mixing the two, I'm not sure really gets you much of anywhere. But even with the T6, in most cases, and especially on the engines that have the exhaust gas recirculation, we're seeing that oil just be so contaminated by the time you get to like 4,000 miles. The oil still has good lubrication, but it's black as the ace of spades, and if you test strip it, it's got a lot of acid in it, and you're wanting to change it to get the contaminants out of your engine, not because the oil's really broken down. But on the engines that run that exhaust gas recirculation, you're seeing so much higher temperatures that because of the temperature, a lot of the manufacturers are specifying them, and I go with that specification of using the synthetic. On the engines that don't have that exhaust gas recirculation, where you don't wind up with those excessive high temperatures, we're really not seeing a lot of advantage to the synthetic motor oils. No, other than the cost of the oil is probably the only drawback. But this has been extremely rare, but we have seen a few engines that were converted to synthetic and they started using oil. And we've guessed that had something to do with the way the rings had been broken in using the other oil, and it was passing the synthetic past them, but that's been very few engines. But we've probably seen half a dozen engines that had been running standard Rotella T4, the mineral, and there again, all of the engines I'm thinking of didn't go to Rotella T6, they went to AMSOIL synthetic. But with the AMSOIL synthetic, they were burning oil like crazy. They were having to add 2 or 3 gallons between oil changes. And after converting them back to the T4 Rotella, it took 2 or 3 oil changes before they quit burning oil. I don't have a great explanation for why, but that's what I've observed.